Welcome to The Explainer. Listen, if you're getting ready for a big exam, maybe even your dissertation defense, you need to be a true expert. So today, we are building your foundation in the fascinating and absolutely critical field of aerosol science. Let's get into it.
So, what's our game plan? First, we're going to nail down what an aerosol actually is. Then we'll get into why these tiny little particles have such a huge impact on, well, everything. We'll learn the specific language, the vocabulary, and then dig into the properties, especially size, that really unlock how they behave.
All right, first things first. You can't master a subject until you've got the most fundamental question locked down.
I mean, at first glance, those things have absolutely nothing in common, right? A volcano, a welder's torch, a virus. But the hidden connection? They all involve aerosols. Tiny particles, either solid or liquid, just hanging out in a gas. They are everywhere.
Now this is the definition you have to burn into your brain. An aerosol isn't just a little specks of dust or mist. No, it's the entire system, the particles and the gas they're suspended in. That distinction is so important.
And this table here really helps put it all in context. You know, you see stuff we're all familiar with, like foam or a gel. But look at that top row. An aerosol is specifically a liquid or a solid suspended in a gas. It's actually the exact opposite of something like foam, which is a gas suspended in a liquid. See the difference?
Okay, so we know what they are. But why should we care? I mean, why is there a whole field of science dedicated to these tiny little suspended particles?
Because their impact is just massive. On a global scale, they are literally at the heart of our climate. They form the clouds that give us rain. They're also responsible for carrying pollutants from one continent to another. But it's not all bad. They can also be incredibly useful. In medicine, they're used to deliver life-saving drugs. And in industry, they're key to making everything from the paint on your walls to the fiber optics that bring you the internet. And here is the central paradox of aerosol science. And honestly, I think this is so cool. The particles themselves, they often make up a ridiculously small fraction of the whole system. We're talking less than 0.00001% of the mass. It's almost all gas. And yet, that tiny microscopic fraction of particles is what drives the whole system's behavior and its impact. It's wild.
Okay, let's keep building. If you want to be the expert in the room, you have to speak the language. And when it comes to aerosols, not all solid particles are created equal. The words we use, the specific terms, tell us a whole story about where they came from.
So first up, we've got dust. The key word to remember here is mechanical. Think of dust as a top-down process. You take something big, like a chunk of rock, and you crush it, grind it, or break it down into smaller bits.
A perfect example is cutting granite for a countertop. That process literally rips solid, irregularly shaped particles right off the block and throws them into the air. That's dust. And these particles can be all sorts of sizes, from superfine to big enough to see with your own eyes. Now, let's contrast that with fume. If dust is top-down, then fume is bottom-up. You start with a material that's so hot it's turned into a vapor, a gas. Then that gas cools down and condenses back into solid particles. The textbook example here is arc welding. That intense heat vaporizes the metal. As that hot vapor hits the cooler air, it instantly condenses into these teeny tiny primary particles. But they don't stay alone for long. They crash into each other and stick together, forming these complex branchy structures we call agglomerates. And rounding out our big three is smoke. The key word for smoke is simple: combustion. It's that visible aerosol you get when something is burning but not burning completely. A coal power plant is a great example. When you burn coal, it creates a visible cloud of fine particles, stuff like fly ash. These particles are usually really small, and just like fume, they love to clump together to form larger structures. Okay, I need your full attention for this next part, because it is without a doubt the single most important concept in all of aerosol science. If you remember one thing from this whole explainer, make it this. When it comes to an aerosol particle, size is everything. It controls how it moves, where it ends up, and what it does when it gets there.
So let's try a little thought experiment. This is exactly the kind of question a committee might ask to check if you really get the fundamentals. You've got two options: one single, relatively large 10 micrometer particle, or 1 million teeny tiny 0.1 micrometer particles. Which group has more total volume?
It's a trick question. The answer is, their total volumes are exactly the same. How is that possible? Well, remember, volume scales with the diameter times cubed. The big particle's diameter is 100 times larger.
And 100 times 100 times 100 is 1,000,000. So that one big particle has the same volume as 1,000,000 of the little ones.
Okay, but here comes the really important question. Which one has more total surface area? And this matters a lot, because the surface is where the chemistry happens. It's where things condense. It's where all the action is. And here's the jaw-dropping part. For the exact same amount of material, the 1,000,000 tiny particles have 100 times more total surface area than the single large one. This is it. This is why a cloud of fine flour dust in a mill can be explosive, and why fine particle pollution is so dangerous. It's all about that massive surface area.
All right, so to really get the full picture of any aerosol system, we just need to add a couple more key properties to our mental toolkit, right alongside particle type and size.
We've also got to think about shape and density. Now, liquid droplets, they're easy. They're always spheres. But solid particles can be all sorts of weird, irregular shapes. So to make the math work, we often use something called an equivalent diameter. It's basically the diameter of a perfect sphere that would act the same way as our weirdly shaped particle. And density is similar. A solid chunk of material has its normal density, but a clumpy fume agglomerate, it has a much lower apparent density because of all that empty space between its branches.
And finally, there's concentration. How much of this stuff is actually in the air? We can measure this two main ways. First, there's mass concentration. That's the total weight of particles in a certain volume of air. Think air pollution standards. But sometimes it's not the weight that matters, it's the sheer number of particles. For that, we use number concentration. This is super important in places like a semiconductor clean room, where even one single tiny particle can completely destroy a microchip. And there you have it. That is the bedrock of aerosol science. You now have the core definitions, you know the lingo, and you understand the fundamental principles that govern this whole invisible world. You know, the first step to mastering any subject is just learning to see it clearly. So next time you see dust dancing in a sunbeam or smoke curling up from a candle, stop and think, what's really going on there? What invisible particles are shaping your world right now?